Hey there. Hey, welcome back. This video is 6-6. We are talking about washers in this video. Again, we're taking volumes of solids formed by rotating a function around a line. And we just looked at disk methods. Again, generally those are with rotations about axes. And then now we're going to take a look at a washer method, okay? So, I first want to start out with kind of, again, your prior knowledge. In example 3, it says set up integral for volumes of solids formed by revolving the region bounded by the line y equals negative x squared plus x and y equals 0. So for part A, it says about the x-axis. So again, our volume is equal to pi times our limits from 0 to 1 of the radius squared. Now our radius, okay, this distance from our axis of revolution to this point here is going to be our function. So negative x squared plus x, okay, squared. So pi r squared, and this is dx. Okay, so there's our first example. Now what you're going to see for part B is I am not rotating about an axis. I'm rotating about the line y equals negative 1, which they've drawn in here. And just to give you an idea of what's going on is if I have this function, okay, and I want to rotate it, it's going to rotate all the way down here and then back up here. Okay, and then I have this area here, this little region represented as kind of a little r, and notice that it has a gap, that there's nothing there. So what we get is something that looks like this. Okay, and you can kind of envision the solid is going to look like a washer. Hence, it's called the washer method, right? You know, when you're putting like screws and nuts together and you have the washer, the little tiny thing in between. Okay, so that's why this is called the washer method. So how do we go ahead and calculate? Actually, I think I'm going to leave that. How do I calculate the volume utilizing the washer method? So here it is. The volume is equal to pi r squared. Well, to get your radius, you have to take the big R squared and subtract the little r squared. Okay, and again, it's dx or dy depending upon what we're rotating about. All right, so r, the big R, that is your outer radius, and little r is your inner radius. So let's go ahead and look at this example here. So for these problems, what I suggest is figure out, first of all, what is your big R, and then what is your little r. So in this case, R, now I'm going to have to erase my beautiful drawing. Big R is the distance from the my x-axis to, or sorry, from my function. This got cut off. This should go to here. Okay, so from my function all the way down. All right, so that is my function. Right, that's this distance. So negative x squared plus x plus this whole distance here, which is 1. Okay, so there's my outer radius, right? The distance from here all the way down. Okay, now I have to take the inner radius, which is from the x-axis down to my axis of revolution, and that distance is just 1, right? Distance is always positive, absolute value of 1. So I have my big R, I have my little r, so volume is equal to pi times the integral from 0 to 1 of radius squared. So big R squared, which is negative x squared plus x plus 1 squared minus little r squared, which is 1 squared dx. Okay, so there is your integral, and that's it. All right. C, now we're rotating the axis of revolution up. So now here it's up at 2. Okay, so again, just ask yourself, what's big R? Okay, so that's from the bottom of my function to, close that. Okay, from the bottom of my function all the way up to here. So this is big R. Okay, so, well, that whole distance, right, is just 2. All right, so there's the big radius. Now we have to go ahead and calculate our small radius. And I have r is equal to, again, that's the distance from our axis of revolution to the kind of the closest point of our function, right? So this is going to be the distance of 2 minus whatever our function is here. So that's negative x squared plus x. Okay. And if I kind of clean this up, we have 2 plus x squared minus x is our little r. Okay, so here our volume will be pi times the integral from 0 to 1, again, of our radius squared. So r squared, or big R squared, sorry, I don't want that, big R squared, 2 squared minus your little r squared, which will be 2 plus x squared minus x dx. Oh no. Here we go. Dx. All right. Okay. Let's go ahead and look at another example. Here we go. So again, set up integrals for the volumes of the solids formed by the revolving the region bounded by y equals x squared and y equals x plus 2. And here they want us to revolve about the x-axis. So again, ask yourself, okay, what is my big R? Okay, and what is little r? So in this case, the big radius, right, I'm rotating about this axis. Okay, your big R is going to go from here all the way to here. So that would be my top function, which is x plus 2. And my little r, okay, that's going to be this distance, which is y equals x squared. So that's x squared. Okay, so again, our integral volume is equal to pi times the integral from, okay, and we need to know our bounds. So I don't have my bounds. Let me write this in first. So I have x plus 2 squared minus x squared squared dx, and I need my limits of integration. So notice here they don't tell us exactly, but in order to find the limits, I can go ahead and set these functions equal to each other and then find their intersection. So x squared is equal to x plus 2 gives us x squared minus x minus 2 is 0. X minus 2 x plus 1 gives us x is equal to 2, x is equal to negative 1. So there are our limits, negative 1 to 2. Okay, and I mean you can kind of tell. All right. Next example. Here now they want us to rotate about the line y equals 4. So here's my rotation. Notice I have this gap in between my line of rotation and my function. So that's what tells me that it's going to be a washer method. And again, we need to ask ourselves, okay, what is our big R? Okay, and so from the line of revolution to the bottom of my function is this whole distance here, which looks to be 4 minus r is equal to 4 minus x squared, right? So it depends upon where you are. If I was measuring from here to here, right, this is big R, okay, that's x squared from 4 all the way to here. Okay, now what is little r? Well, my little r is this distance from 4 to this function. So again, 4 minus whatever this function is, and that line is x plus 2. Notice I put the x plus 2 in parentheses because after I clean this up, we end up getting 2 minus x. So that's little r. Okay, so thus our integration will be from pi times, again, negative 1 to 2 of big R squared, so 4 minus x squared squared minus little r, which is 2 minus x squared dx. Okay, and that's it. That's just setting up utilizing the washer method. Lots of r's. I mean, how many times did I say r in that video? Man. Hey, my SS talks about a joke, right? This must be the pirate's like favorite video. Lots of r's, right? But what's a pirate's favorite letter? Ha, you think it's the R, but really it's the C. Right? You like that one? Huh? Huh? Good. Right? Just like a Soldier Boy. Sorry, I guess that's my time to go. Soldier Boy, what's Soldier Boy's favorite letter? You got that one right. Good job. All right. Hey, so just a quick little note down here. When finding volumes using either discs or washers, make sure you sketch it and draw a representative rectangle. This will help you decide, do I need to use dx? Do I need to use dy? Remember, if it's up and down, vertical, perpendicular to the x-axis, dx. If it's horizontal, dy. All right. Also, too, the figure will help you decide, do I need to use a disc or do I need to use a washer? If you are just rotating, right? If I have an object like this and I'm just rotating it, okay, that's going to be completely solid. That's going to be a disc. Now, if I have a gap, right? So I'm rotating it about, right? But there's going to be an empty space in the middle. That's going to be a washer. All right. Catch you next time. Peace.